Today I'll be covering the evolution of GNSS and its relevance to the auto EV. So we started out with the global navigation system. That consists of the GPS, which was the original American system developed almost 50 years ago. Then the Russians came along with the GLONASS system. We then had the European system Galileo, and finally the Chinese system Beidou. So we also have regional systems, the QZSS and NAVIC. NAVIC is the most recent one. Those are regional systems directly above those particular countries. We started off in the high band, the L1 band on the right-hand side. Recently, in the last few years, there was an introduction of a L2 band. So many products are developed into that region. So we have L1 plus L2. So the evolution has been to multi-constellations, where you have multiple constellations across the world, and then multi-band, so L1 plus L2. What we did at our company is we went directly to the L1 plus L5 band, which is modernized and more advanced than the L1 plus L2 band. And then nowadays we also have triple band. So we have receivers that can handle L1, L2, and L5. The advantage of having multiple constellations can clearly be seen in this slide. So this is an example of the original system where you have GPS plus QZSS only. So this would have been a view in the city of Japan and looking up skywards. And today on the right-hand side, we can see there's a plethora of satellites from Beidou, Galileo, GPS, and GLONASS. So we have a lot of more satellites. And where we see the advantage of this is a typical inner city scenario. So here you have 3 GPS satellites only. The fourth one is going behind the building. If that goes behind the building, you will lose the signal. So you cannot compute position fixes with less than 4 satellites. So in this case, in Japan particularly, we have the QZS constellation, which would then augment that system. You'd have 4, 5, and 6. You could continue positioning. But the reliability of that positioning would be questionable as you go in between all the other buildings. So in this case, this is today's scene. We have a lot more satellites. You have a lot more resilient positioning in that particular case then. So if we look at the errors inherent in the system, we've got satellite orbit error, which contributes around 2.5 meters. You've got satellite clock error, which is another 2 meters. You have ionospheric delays, around 5 meters, tropospheric delays, around 0.5 meter. And then you have multipath, where the signal is reflected off a building and then takes longer to get to the receiver. In that case, the signal's longer, the distance calculation can be out. We also have antenna design being critical for the solution to be accurate. So if we look at the error bands from each satellite, and those correspond, we end up, if we have satellites, a wide distribution of satellites, good satellites that we can choose from, we end up with a much more accurate position on the ground. In the case where we have a poor antenna design, we only look at the satellites directly above us. In that case, we then have a much wider range of errors. So antenna design is extremely critical in any GNSS product. In terms of our choice, we've gone for the high band and the low band, L1 and L5. So we have some advantages in that. If we have 2 bands, we have the same signals at the same time coming from the same satellites on different frequencies. We can cancel some of the ionospheric and tropospheric effects from the solution, and we can have then a much more accurate position on the ground. So we end up going from 2.5 meters to 1 meter accuracy using the L1, L5 combination. So we recommend all of our customers to look for solutions with L1, L5. Of course, RNSS Navic only uses alpha. One of the other ways that we can reduce the errors is having stationary base stations. Those stationary base stations can collect the same information as the roving device, and we can then correct for some of the errors in the system as well. So we can go from meter level accuracy to centimeter level accuracy. This is an indication of a network where we have correction stations all around where there's a green dot. The very important thing to do when you're selecting a correction station partner is to ensure that there's consistent support. So you have to have matching constellation and band support on your network that matches your receiver. This is an indication of a receiver with a standard precision positioning in the red circle there. As it goes to float mode, it'll be the decimeter level accuracy. And when you see down at the centimeter level accuracy in green, that then is an RTK fixed solution. India is changing rapidly. Every time I come here, I see higher bridges, I see overhead trains going in, I see higher buildings going up. And this is a very challenging environment for GNSS. So if you look at this particular case, there's a train overhead, there's trees on the left-hand side. GNSS is an open sky technology, so the GNSS will actually struggle in that environment. For this reason, we incorporate dead reckoning onto a lot of our GNSS devices these days. So dead reckoning is the combination of an IMU. The IMU has a 3-axis accelerometer and a 3-axis gyro, and that can give you inertial measurements on the vehicle. If you go into then a tunnel, or if you go into an area where you have a high level of obstructions like this, the GNSS can carry on computing estimations of the position based on the inertia of the vehicle rather than the measurements from the satellites. So module partner choices in the EV sector. We recommend L1, L5 receivers. We suggest you use compatible series that can offer you multiple use cases with RTK, with DR, without RTK, L1, L5 combinations. Of course, those solutions have to be cost effective. In India, they need to be suitable for AIS 140 and suitable for the upcoming tolling projects. Along with the modules themselves, we always suggest also that you partner with somebody that can provide the antenna services, somebody that can provide the cellular connectivity, somebody that can provide the RTK services for the base stations, a range of modules in terms of GNSS, and then of course the high precision algorithms and an ability to do design reviews on your design. This is a video of a typical DR test. So in red we have a standard GNSS, and green we have a dead reckoning capable GNSS. So as you see, as he goes in underneath the obstruction, you'll see the standard GNSS deviates. Obstruction there, and the standard GNSS deviates, whereas the DR GNSS continues positioning accurately. So these are all difficult environment examples. You can see underneath the rail, in amongst the trees, lots of other vehicles on the road, so those signals are blocked. Having DR on board makes the solution continue to be accurate. So here under dense tree covers with tall buildings on either side. Here he's going under overhead highway. 50% of the sky is blocked off, so we're losing 50% of the satellites, but yet we can maintain the positioning. in through a tunnel where the GNSS signal's blocked completely. You can see the red deviates quite considerably, the green continues through. And here's a long tunnel. This is a good example. So you can see here, the standard GNSS will stop completely, while the DR GNSS continues navigating through the tunnel. So even though we're not receiving any satellite signals, we can navigate through that scenario. Again, in a multi-level parking, this is an extreme case. We can see that the standard GNSS deviates quite considerably, while the DR GNSS continues tracking accurately. So India's urbanizing rapidly. You have tolling projects coming. You have the AIS 140 project already in multiple years. We see DR as becoming an essential element of that equation, where the DR is added to the GNSS, and our modules are now made in India. So all of our AIS 140 modules are made in India. And you need to go into the future with your ability on the GNSS. You can embrace the future with much more modern vehicles. Thank you.